In Lesson 1.9, as you can see, we're going to be solving systems of equations in 3 variables, and we're going to use the elimination method as our primary means of doing this. So in the first objective that I have, that's literally what we're going to do. We'll be handed a system of equations in 3 variables, and we're going to be asked to solve for each of those 3 variables. And then as we've gotten a taste of that, then we will move into some real-world problems where we have to set up the system and then solve it. So let's just jump right into an example, and I'm going to give you a step-by-step process of how to solve these 3 variable systems. It's always a good idea to look over your system and try to pick out a variable that looks like it would be the easiest to solve for. And in this particular example, I would go for y as my variable to eliminate. It looks like it would be the easiest process. Now, you're not going to be wrong if you choose x or z. It's just that in some cases there's an easier path than others. So in this case, I think the easiest route to take will be to eliminate y. So as my step 1 says, after I've identified y is going to be eliminated, I'm going to set up 2 pairs of equations. So obviously I only have 3 equations. If I'm going to set up 2 pairs, one of these will be used twice. One will be used in each pair. So just think about the top and the middle equation being put together. We'll write that out. So here is the first and the second equations. And then I'm going to combine the second and the third equations. Negative 4x plus y minus 5z is negative 36, and 5x minus 3y plus 3z is 31. Okay, and then an important next step is to eliminate the same variable within each pair. And we've already established, we looked ahead and we know that y is going to be the variable to eliminate. So the way I'm going to eliminate y in this left pair is I'm going to multiply by 2 across the bottom, and then I'm going to add the 2 equations together to eliminate y. So I'm not going to do anything to the top equation. And I'm going to multiply by 2 on the bottom to create opposite terms with y. So this is going to be negative 8x plus 2y minus 10z is negative 72. All right, and we can go ahead and add. I'll just put a little plus here to remind us that we're going to be adding all the way across. 3 plus negative 8 is negative 5x. We get 0 here, of course. 4 plus negative 10 is negative 6z. And then this becomes negative 37. Okay, same idea over here. We've got to eliminate y, but a little different way of doing it. This time we're going to multiply by 3 across the top, and then we'll add to eliminate y. So the top equation times 3, negative 12x plus 3y minus 15z is negative 108. And then I'm going to leave this bottom equation as it is and add all the way across. Negative 7x, y is cancel. Negative 15 plus 3 is negative 12z. And then negative 108 plus 31 is negative 77. Okay, so now I'm going to move on to my next step, which is going to involve putting these 2 equations that remain, both of them are xz, we're going to put those together in a system, and we're back to familiar territory. We just have a 2-variable system, and we can use elimination to solve. So I'll just rewrite these. Negative 5x minus 6z equals negative 37, and negative 7x minus 12z equals negative 77. All right, and so pretty obvious that the best choice for elimination will be to eliminate z, and I can do that by multiplying either by 2 or negative 2, depending on whether you want to add or subtract. And I'll just do negative 2 across the top equation. Nothing will be done to the bottom equation, and that will force opposites so that when we add, z will be eliminated. So this will be positive 10x plus 12z, and negative 37 times negative 2 is 74, and the bottom equation will remain the same. Okay, so when we add all the way across, we get 3x equals negative 3. So we found our first variable, x is negative 1. Okay, so now you can think of just backtracking through your work. We're on step 4. After we found that first variable, we're going to substitute for x in this case, or whatever the variable happens to be that you solve for first. Go back to where you have 2 equations, and you will replace x in this case, and that will enable us to find z. So it really doesn't matter which of these you pick. Make that z a little plainer. I'll just go with the top equation. Again, it really doesn't matter. So negative 5 times negative 1 minus 6z is negative 37. 5 minus 6z is negative 37. Negative 6z is negative 42. So z is 7. All right, so 2/3 of our answer is complete. And now we're going to go all the way back. Our step 5 will be to go all the way back to the original system where we had the 3 variables. And we substitute for, in this case, we have found x and z. So we just pick one of those 3 original equations, it doesn't matter which. Find the one typically that looks like it's easier to work with, and let x be negative 1 in this case, and z will be 7. So maybe we'll just go with the bottom one. X is negative 1, z is negative 7. Negative 5 minus 3y minus 21 is 31. Negative 3y minus 26 is 31. And I just realized I put negative 7 and it should be positive 7. Sorry about that. So this should be plus. So one area of this, you can see where there's quite a bit of time and effort spent in solving these. So just word to the wise, be very careful. One little mistake, obviously, can mess things up for you. So negative 3y is, if we subtract 16, is equal to 15. And y is equal to negative 5. So the answer will be presented as an ordered triple. And you just put them in order. X is negative 1, y is negative 5, and z is 7. And that's our answer to this first example, solving by elimination. Okay, let's move on to a couple other examples that represent what we might call kind of unusual situations. We're still going to go through the same thought process, and you try to identify a variable that looks like it might be the easiest to eliminate. And in this case, I don't really see anything that just jumps out as being easier than the others. I'm just going to match up the top 2 as a system. 5x plus 4y minus 5z is negative 10. Negative 4x minus 10y minus 8z is negative 16. And then I'll match up the bottom 2. Negative 4x minus 10y 6x plus 15y plus 12z is 24. Okay, so we're going to eliminate the same variable within each, and again, you don't really have a wrong choice, but sometimes there's a better choice than the others. I think I'm just going to eliminate x in both cases, multiplying by 4 and -5, or -4, +5. You can do either one. So let me just illustrate multiplying by 4 and -5, okay? And with the intention of eliminating x. Okay, so across the top, multiplying by 4, we have, I'll just continue over here, 20x plus 16y minus 20z is equal to -40. And I'll just do positive we'll set up opposites. You could do -5 and then subtract. Either way will work, but most people like to set up addition. So I'll do that. 5 times -4 is -20x minus 50y minus 40z, and that's -80. Okay, over here, I still have to eliminate same variable. I've got to eliminate x, but I'll just do 6 up here and 4 down here. Okay, so across the top, multiplying by 6, that's -24x minus 60y, 48z, -96, 24x, 60y, 48z, and 24 times 4 is 96. Okay, so this looks interesting. So if you notice, our right pair, we'll start here. You probably figured out that all of these cancel, and we're left with the statement 0 equals 0, which is true. Now let's jump over here. The x's, of course, cancel, and we're left with -34y minus 60z is -120 as we add across. Okay, so I wanted to give you a heads up about this particular situation where one of your pairs will yield a true statement like this, and the other pair just represents the equation of a line. And so this represents the fact that all three of these would converge at the same line. These are representing three different planes, and they would all converge into the same line. And so any ordered pair that happened to fall on that line would represent a solution to the system. So this is the case that we call the infinite number of solutions. And this is a perfect example. You have a true statement out of one of your pairs, and then the equation of a line in the other pair. Or it could be that you maybe have two true statements, and that would also represent this same situation. You would just interpret it as an infinite number of solutions. Okay, well, let's take a look at this one. Take a look over the system and see if there's a way, a better way. So I'm going to do this. I'm going to target this z because it just has a coefficient of 1. So I'm going to do my two pairs as the first and the second, and then I'm going to pair up the first and the third. Okay, so that's going to look like this. 3x plus 5y minus z is 12, paired up with the middle. -2x minus 3y plus 5z is 14. and we're going to intend on eliminating z. So here's my first equation again. So you can pair these up whatever it takes in however way you want. I mean, obviously you're limited, but as you can see, this is an example of first and second paired, and then the first and third paired up. All right, and so to eliminate z, I'm going to need to multiply by 5 across the top. So here's the top multiplied by 5. 15x plus 25y minus 5z is 60. And I don't have to do anything to the bottom. Negative 2x is 3y plus 5z is 14. And I'm going to add all the way across. I get 13x plus 22y is 74. Okay. Over here, I'm going to multiply by 3 across the top. And that gives me 9x plus 15y minus 3z is 36. And 4x plus 7y plus 3z is 38. And adding all the way across, I get 13x plus 22y, and those cancel, and that equals 74. Well, here's another way that the infinite number of solutions presents itself. Obviously, you can see where we end up with the same equation in both cases. If we did try to put these together as a two-variable system and eliminate, we would get a true statement, which would be 0 equals 0. So a little different way of showing it, but it's the same interpretation. This is also going to be your infinite number of solutions scenario. So you will have one. I purposely gave you one problem that will be a no solution, and you'll spot those pretty easily. When one, you try to, you go for that variable to eliminate out of your two pairs, and one of your statements is false. You know, maybe you get down and you eliminate, and it ends up something like this, where 0 equals 6. Obviously, that's not the case. So if you end up with a false statement in any way with either one of these pairs, then that makes your answer no solution. But I wanted you to have a look at what two different ways that infinite number of solutions could appear in your answer. Okay, so I wanted to get you set up anyway on this word problem number 18, because it's problems like this that are really, to me, more beneficial. It's good to know how to take a system that you're given and solve it, but it's even better to be able to set the system up yourself. So let's read through this. You have the posted results of a recent high school swim meet. Say that 24 individuals placed, earning a combined total of 53 points. First place had 3 points, second place 2, third place 1. There were as many first place finishers as second and third combined. So I just want to set this up for you, and then I want you to use, you can use elimination, and I'll show you also how you can also use substitution if you prefer. Even though I know our previous examples didn't use substitution, but it's really not bad to do. So first of all, let's see if we can set the system up, and that begins by identifying variables for the whatever it is that the problem is asking us to do. And it says an equation that represents how many people finished in each place. So I'm going to say X is first place finishers, how many finished in first place. Y will be second place finishers. And Z will be third place. Okay, and I think I'll just color code maybe how we're getting the equations from certain phrases or sentences. Okay, so it says in this first phrase, the posted results said that 24 individuals placed. Okay, so I'm going to use a blue equation to represent this part of the paragraph. So I had X many first places, I had Y many second places, and Z third places, and that should be a total of 24 that placed. So that's one of my equations. Okay, I've got another equation. Maybe we'll go with green. Notice that one equation will deal with the number of total points earned. So we're told that first place is 3 points, second place 2, and third place 1. Okay, so I'm going to say 3 points times the first place finishers, 2 points times the second place, the number of second places, 1 point for the number of third places, and that should total 53 points. All right, very good. And then finally, I guess we'll just do black. This last sentence contains information for our third equation. There were as many first places as second and third combined. So that's pretty easy. We just say the first place finishers were equal to the sum of the second and the third. So you can do this if you like. I'll just give you a quick glimpse into substitution in just a second. But if you wanted to use elimination, you could just take this last equation and line up the variables. You just make it equal to 0. X plus Y plus Z. I'm sorry, X minus Y minus Z is equal to 0. So you wouldn't really use this form. You just mark that out, and you're back to elimination. That would be easy enough. But you could also do this. Let me just throw this out at you. Maybe you're interested in doing substitution. Since this bottom equation is already solved for X, substitution says that you can take this and replace X in the blue and in the green. And then when you simplify, you'll have two equations that only have two variables. They'll be in terms of Y and Z. And so then you take those two equations and you're back to regular two-variable elimination. So that's a possibility as well. Substitution is really nice when you've got one of the variables already solved for, but you don't have to do that. Again, if you want to go ahead and just set this up equal to 0 and use elimination, that's fine. But I wanted to set it up for you and see if you could come up with the final answer to this one. And then you have this challenge problem that I thought would be good to think about. And if you're told the general form, or sometimes we call the standard form of an equation for a parabola, is provided, y equals ax squared plus bx plus c. And you're told that there are 3 points on a parabola. One of them is 2, -10. One of them is -5, -101. And the other one is 6, -90. Okay, so they want you, if these are 3 points on a particular parabola, they want you to come up with the exact equation for this parabola. So I'm going to get this one started for you as well, and then I want to see if you can use, you'll probably want to use elimination on this one. But notice if we're given 3 different ordered pairs, 3 points on the parabola, this is x and this is y, then we're going to plug in for x and y, but we're going to do it 3 different times. Okay, so it's going to look like this. -10 is equal to a times 2 squared. Notice how I'm putting 2 in for x. So I'm just going to say 4, 2 squared, plus B times 2 plus C. Okay, and I'm going to do that same thing with this next ordered pair. Negative 101 equals A times, this is going to be negative 5 squared, which is 25, plus B times negative 5 plus C. And then finally, we'll plug in again. Negative 90 equals A times 36 plus B times 6 plus C. So to turn that around, the system really that you're going to be solving is, we'll just write it the way we typically look at it. 4A plus 2B plus C is negative 10. 25A minus 5B plus C is negative 101. 36A plus 6B plus C is negative 90. So this becomes your system that you're going to solve. And when you're finished, obviously you're going to be finding A, B, and C. But don't just stop there. Don't just leave it as the ordered triple. When you found those numbers, then you're able to substitute in for A, B, and C in this equation form, and your answer should look like this. It's actually the equation for this particular parabola with specific numbers plugged in for A, B, and C that you found from solving this system. Okay, so I want to just kind of set that one up for you and see if you can take it all the way to the end. Obviously, the easiest method to use here is to use elimination and eliminate C. But see what you can do with that one. That was kind of a good problem. And I hope this will help you with the assignment. And if you have any questions, let me know.